Hello and welcome to Easy Projects. So in this video I'll be starting a project that I've been wanting to do for a very long time. So pretty much every time you work with electronics you need power of some kind, and we tend to use power supplies because they're nice and easy. A long time ago I made this power supply, which is just an LM350 voltage regulator and a 10-turn potentiometer, some binding posts and a load switch. It works nicely, but it doesn't have any constant current or current limiting function, and the display is only has one decimal place. After I built this one, I wanted to make another one that had the constant current as well, but I never got around to that because I found this HP power supply cheap on the internet and I bought it. But it has one problem, and if you've seen my videos you know what it is. The fan is freaking loud. So of course I thought about it again, and some time back I saw this power supply on eBay, which was also pretty cheap, so I bought that one. And when I turned it on, I thought, yay, it's silent. No, it's not. And it gets even louder when you put a load on it. So when I'm just working by myself it doesn't bother me that much, I can live with it. But when I record videos the noise is very annoying on the videos. So I want to make one that has the same functionality as these, but the fan should only kick in when it needs to, so when you draw a lot of current. I think we still need to have a fan, but on low currents it should be silent. So it's going to be a linear power supply, just like these, and I want it to be at least 25 volts and around 3 amps, so just in between these. Of course, the first step to make a linear power supply is to get a transformer. And I got a few of these laying around, different varieties. So this one is 24 volts at 3 amps. If that's 24 volts AC, we'll get a bit more DC, of course, because we multiply it by the square root of 2 to convert from the RMS to the peak value. And then we'll have to subtract a little bit from that to allow for some ripple and drop out of the regulator that we're going to make. But anyway, we should be able to get around 25 volts DC out of it when we're done. It has one limitation though, because when we want to run it without a fan, we have to think about how much voltage we drop across the power transistor. And this only has a single output of 24 volts. You can get other transformers that maybe have two outputs of 12 volts, and you can put them in series to get 24. So I got this transformer out of some old equipment. Can't remember exactly what it was, but I remember it gave around 30 volts AC in total. But we have two sets of coils here, and we get 15 volts AC on each. And having these two taps, we can make a configuration like this, where if we leave this as it is, we only use one of the coils on the secondary, so we get 15 volts AC here, goes through the bridge rectifier, and we have a big storage capacitor here. And say we have a load of 5 volts, that will drop, let's just call it 10 volts across this transistor, and if we use 1 amp that will dissipate 10 watts. But it's still much better than if we had the full 30 volts, because then we would have 25 volts across this with 1 amp of current, and that's 25 watts. So by doing this we can use a smaller heatsink, but we will need some intelligent way of controlling this switch. It should be a relay, of course, or we could do it with FETs as well. But we need some way of controlling it so that when the output voltage is set to a certain value, it should switch up and use the full range. And when we drop back below some value, it should switch down to this one. So if I remember correctly, this is something like 5 amps, this transformer here. But I have another one that's 3.2 amps, I think it is, or 2.8, just around 3 amps. I might use that one instead. It also has the two secondary windings, which we want. So this time I want to make the power supply entirely from scratch and just use discrete transistors and op amps and whatever we need. And if we first take a look at the voltage regulating part, it's fairly easy to understand, at least in theory. All we need is a transistor and an op amp. So we'll connect the op amp here. So we connect the inverting input to the output of the power supply, and we have a set voltage down here. And if we remove this part and imagine there's a line here, you can see it's just an op amp buffer. So basically an amplifier with a gain of 1, and that will make sure that this voltage is the same as this voltage. So if you want 5 volts out, you put 5 volts in here. And this is very high impedance and this is very low impedance. So you could feed this voltage from a potentiometer or something like that. But usually we want to use a voltage reference to get a nice and stable output that doesn't fluctuate over time. And the good and precise voltage references are not very high in voltage, or you can get that, but usually it's from 1.25 to say 5 volts for the good ones. But of course, if we can only put 5 volts in here, we can only get 5 volts out. But since we're using an op amp, we can just add some gain in the negative feedback here. And if we want 30 volts out, we can just multiply by 6. And that should allow us to use 5 volts down here. So in case of a 5 volt voltage reference, we would do a configuration like this. That would allow us to control the output from 0 to 30 volts. It might be a good idea to throw a resistor in here, of course, but you should get the point. So this is kind of the idea we're going to use for the voltage regulation, but of course we need to make some current regulation as well. And to regulate the current we need to measure it somehow. And the easiest way to measure current, of course, is to use Ohm's law. If you have a resistance with a current through it, we'll have a voltage drop. And we can use a shunt resistor. It's a very low value resistor that has terminals right at the beginning of the resistance inside the package, so we measure directly across the resistor so we don't get any loss from the leads. If we use this, we can measure a precise voltage that indicates how much current is flowing. So if we say this is 0.1 ohm and we have 30 volts in and say I equals 1 amp, then we will drop 100 millivolts on this one, so we'll have 29.9 volts out. So you see here that this is a differential measurement. We can't just measure one point. So to get it to work with our system over here, we need to convert it to a single-ended so that it's referenced to ground. So instead of measuring 29.9 volts, we will measure the 0.1 volt that we actually drop here. And we can then feed that into an op amp and do something with it. Depending on the precision that you want, you can buy dedicated ICs to do this exact job of current measurement, or you can use a differential amplifier, which you can make from an op amp. So you could do something like this. This is a standard differential amplifier, but you will need a very good rail-to-rail op amp to do this, because we are dealing with basically a few hundreds of millivolts, and it's all down at the ground level. It is entirely possible with a good and expensive op amp, but you could also fix it in other ways. You could increase this by a factor of 10, for example, use a 1 ohm resistor, but you'll start to dissipate a lot of power in the resistor and also drop some voltage. If you have 3 amps, that's 3 volts and 9 watts. You also have problems with the resistor heating up and changing its resistance, so your accuracy will drift a little bit. But that will create a few volts instead of a few hundred millivolts. For low current applications, say up to maybe 1 amp, you could probably get away with 1 ohm here and use a differential amplifier. But I think it's a better idea to use a dedicated IC, and they are actually sometimes cheaper than the op amp you need to make the differential amplifier if you want a good one. You can get a whole variety of different current sense amplifiers that can basically measure from microamps and all the way up to hundreds of amps, depending on which resistor and which amplifier you use. I think the ones I've got take an input voltage, differential voltage of 200 millivolts. So I would have to lower this resistor even further for that one to work. Or I could order another one. It then has a lot of gain. I think it's around 20. And then it will output a voltage up to 5 volts. And also the 5 volt output is much easier to work with than this 0.1. So I'm pretty sure that's what I'm going to end up using. But in theory it is exactly the same as this. It's just fine-tuned to work for that specific application. And if we wanted to make a current regulator out of this, we would just feed it in to the inverting input of an op-amp, and like we did over here, we'll just use the non-inverting to set the reference point. And this will probably only work in theory because, as you might remember, the voltages are very, very low, and you would want to add some gain in here, either in the differential amplifier or in this op-amp here, because else you would need a reference from 0.3 volts and downwards, and that wouldn't be good. So we would probably want a times 10 or times 20 gain somewhere in the loop here. So to make a power supply out of this, we could just remove this and remove the load here, and we could connect it through like that. So this could potentially make a nice and working power supply, but we have one slight problem here. The current control circuit over here will work exactly as we just figured out, given that the input voltage is enough to drive that amount of current. So that depends on the load and the voltage we set, of course. But say we set the maximum voltage and we have a low enough load, we can control the current with this part of the circuit. Say now we want to provide a constant voltage to a load over here. We will set the current to maximum, so we will basically just always have this transistor fully on. And say we set 5 volts here, and we draw 1 amp. It will regulate, so we have 5 volts on this line here. There will always be a little bit of voltage drop across the transistor, and we also have this resistor, which has 0.1 ohms. So at 1 amp, as we mentioned earlier, that's 0.1 volts, so we will get a maximum of 4.9 volts on the output, probably a little bit less because we have some drop in the transistor. So that's not going to be a very good power supply. Of course, there is an easy way around it though. We just cut this wire right here, and we jump across and connect it right on the output. And that actually solves more than one problem, because when this circuit is inactive, we can basically do this, and this will just be fully on. The voltage is red right here, so the output will always be at the 5 volts no matter how much current we draw. And when we go and turn down the current knob here, at some point this transistor will start to switch off, because we're drawing too much current compared to what we set down here. When we do that, the voltage on the output will of course drop as well. And once the voltage drops, this transistor will get turned more and more on, allowing for more current to actually go to this transistor here. Before, when we set 5 volts and we connected it here, we would always have 5 volts at this line no matter what this transistor was doing. So we would have two things regulating at the same time, because this one wants to keep this at 5 volts and this one wants to keep this at a constant current, and that could probably make some oscillations. With this, we make sure that as soon as this kicks in, this will just turn on fully, and we only regulate using this one. And in the other scenario, when we are using constant voltage, this will be fully on and this will be regulating. I'm not entirely sure that this is going to work perfectly, of course, but you can imagine we can also get some strange behavior when this one turns off and this one starts to turn fully on, maybe there'll be a little bit of oscillation in the signal. But it shouldn't be anything that we can't filter out. We can also combine these two op-amps to control the same power transistor, of course, so we don't need this one. We can do with one, just by connecting a transistor to the base of this and pulling it low using either this op-amp here or this op-amp. But we will get back to that later. I think we'll try and build this circuit up in the breadboard and see if we can get it to work.